Okay, so the last video actually, I want to add one extra thing here. It's not just absorption spectra, but absorption and emission. So we are going to be talking about the classification of stars based on what we receive from them. So all that we receive from them is light, okay? And so I've shown you a few sample black body curves before. This is an actual spectra received from Beta Lyrae, okay? And what we have here, the shape of this curve overall, hopefully you recognize it. That looks like a black body curve right there, all right? So we see here that we have some lines dipping below, all right, the curve, and we have some lines going above it. And so what we have here, these are part of the emission spectra that we are receiving. And the things that are going below it, all right, we can take as being part of the absorption spectra. Okay? But what we're going to do, okay, is classify stars. So, what are the different ways in which we can classify stars? We can, a long time ago, the way that they did it, ancient astronomers classify stars according to how bright they were. And that's the easiest way. You look in the sky, which are the brightest ones, which are the dimmest ones, and that's it, all right? But these days we use a bit more sophisticated approach, all right? And so today what we're looking at are the strength of the emission and absorption lines. So we've talked about emission and absorption spectra a little bit from quantum mechanics. Those are all the places in which we have energy levels changing, okay, and photons being absorbed or emitted, all right, between, showing, those electrons jumping between states. And actually, there's some other interactions that's showing as well, all right. Not going to get into that beyond the scope of this class, beyond the scope of my own education, frankly. But the first attempts, though, to use these absorption lines, all right, was done by the increasing strength of the hydrogen lines. So what ended up happening, this was actually done at Harvard by what were called computers, which is basically the only job a female can get in science back in the day before, they were treated equally, or still, they're still not, but treated more equally today at least. And the idea was that they can order them, all right, according to the increasing strength of the hydrogen lines that they saw in the spectra. All right, so here's a sample of the two major. Actually, it's hard to see the colors here. Okay, but you have the two major hydrogen lines there that you can at least see probably on the YouTube video. And they were sorted according to the strength of these lines. All right, and given just the designation, alphabetical order, A, B, C, D, and so on. So what they later realized, actually, and one of the people behind this was this person right here, Annie Jump Cannon, was that it was better to actually organize them according to color and temperature. So they reorganized them with these same letters according to their color and temperature in the following order. Okay, so these are the classes of stars as we know them. So it's actually easy to think of the color in terms of going from hottest to coolest. All right, starting with blue, which is the hottest you can have. All right, and going down here. Remember, the presence of all colors together is white, which is why we don't really have green here. Right, moving on down to yellow, orange, and all the way through red. So you do need to know what colors we have here, but it's not hard to remember because we go from blue to blue-white to yellow, orange, red. Okay, so we know here in between here with the whites, you have the combination of blue, white, and yellow, white, and we're just moving from blue, which is the hottest at O, to the coolest, all right, all the way at M, excuse me, that is red. We're not going to talk about L and T in this class, but I have them up here. So there's a couple different mnemonics, and I do remember these mnemonics that you can use to study their order. This was drawn for me from an old student. One big and ferocious Gyarados killed my little Thomas. I am the little Thomas, even though I am the Charmander, or Chormander, however you want to say it in this picture as well. Artwork deserving of JJ skill, in fact, really here, but this can help you remember it. One of the lame ones that astronomers like to use that works is, "Oh, be a fine girl/guy, kiss me." And that is something that I think a lonely astronomer must have come up with a long time ago. But we're not going, you can use whichever one you want, doesn't matter to me. but I personally, obviously, am completely biased in favor of this little Pokemon one here. All right. So moving on though, but you do need to know their order, and remember that it starts with the hottest, blue, and O. All right. Another image of typical emission absorption spectra for all these different classes of stars. All right. So what we have here, we have the hertzsprungrussell diagram, all right, which helps us to see all of these stars. If we actually take all the stars that we see and place them on the diagram, they form these different regions. Okay. So what they thought was that this might help, okay, and show if there's some sort of relationship actually between their temperature and their luminosity, all right, or between their absolute magnitude and spectral class. So we'll get to talking about what absolute magnitude is in a little bit. So what we end up having here is a graph that shows luminosity versus temperature, all right. It can also be graphed a different way and still get the same results, all right. But the big idea here, right, is to try to show what the relationship is between these two things for stars. And we see that most stars fall within three major regions. So there's three major features that we have here. This diagram does get a bit bigger actually, but we're only going to focus on these three regions here. And so the first region here is that most stars fall on a strip, all right, that extends diagonally from the upper left to the bottom right, called the main sequence. You have that name right here, okay? So that's just, most stars spend their lifetime there. You have another region of very large stars that are going to be orange and reddish in color, right, that occupy the top right here. These are our red giants and supergiants, okay? Now there are also blue supergiants. We're not going to get into talking about these a whole lot, but you just need to know that they occupy this region. You have the main sequence over here, and finally you have very, very small stars that are very small and hot that we call white dwarfs, okay, and they occupy this region over here. So we see that their luminosity is very low, and the reason for that is that they are so small, okay, and there's no more fusion really happening with them. Another thing to point out, this luminosity scale is a logarithmic scale, so every notch we go up, we're going up by power 10. Okay? So, okay, those are the three main regions that you need to know for the Hertzsprung-Russell diagram. Hopefully you listened and were able to write down what I said. If not, pause me, rewind me, and write it down again. Okay? These are and I will be testing you on these three regions here. So let's quickly here talk about the three different the major different types of stars, okay? The main sequence stars here, they produce enough energy to exactly counteract the balance of gravitational pressure, okay? And we see here as the luminosity goes up, the mass goes up with these guys, okay? And this diagram has been drawn very nicely to actually show that, okay? So red giants, they are very large, cool stars with a reddish appearance. All main sequence stars are going to end up evolving into a red giant. Actually all except for some of these smaller little red guys here. But most of the stars here on this sequence will evolve as long as they're above mass of 0.25 solar masses. Okay. So white dwarfs depend on the size, but most were red giants that just ended up throwing off their mass. Okay. Very small size, very dense. Okay, they don't have any nuclear reactions happening. All right, they're shining because of something called electron degeneracy pressure. So actually here, let's show some images here. You have that's right. I told you before. Antares here, comparing this, to our solar system. This being the orbit of Mars, the red supergiant, absolutely enormous. Okay, and the size of our sun, right there, a little dot. Okay. All right, so moving on from here, though, we have what are known as white dwarfs. Okay, this is Sirius A and B. Okay, compared to the size of our sun here, this is a little white dwarf about the size of the Earth. Okay, and I think that Sirius B is the white dwarf there. Okay, and here actually we have another image of this to show you Sirius A, the large white main sequence star, compared to Sirius B there, our little white dwarf. Okay, so we also have some other stars, okay? So these stars are periodic stars, and these are, some of these periodic stars we call Cepheid variables, okay? And we study them, and their luminosity actually varies with time, okay? The temperature, all right, is proportional to the period. Okay, this is period here, not temperature. Is proportional to the luminosity, or how bright it can get. Okay, and we actually use these because of this relationship. We use them as standard candles for the universe. All right. So yeah, that's variable stars in general. Okay, stars. Cepheids are special stars where the temperature, the period is proportional to the period. Variable stars, just stars in general that their luminosity varies with time. All right. We also have, as I said, we have binary stars. Talked about the Sirius system there, A and B, being a binary system. And what it basically is that all stars, probably most stars, are a part of a binary system. All right. And so what they do is they do orbit each other. Okay. Their orbital period is given by this following relationship, which is something that we can derive from Kepler's third law. All right. And in orbital motion, everything we've done with that. All right. So the two of them, they're going to orbit each other, and there's a couple different ways that we can actually determine that a system is a binary system. The first is just visually. When we look up there and it appears that we have two separate stars, and we can actually see through a telescope. Sometimes we can't separate them out with a telescope. We can't resolve them. So the two ways that we can do this is that we can have an eclipsing binary. And this is our eclipsing binary right here, where we have one star moving in front of the other. And every time that happens, you have a decrease in the intensity. So you actually see a dip as you move through in time as that star goes in front of the other one. Okay? So that's one way. That's what's called an eclipsing binary. And the other here is a spectroscopic binary, okay, where we actually have the Doppler effect, which is what's going to cause a shift in the redshift of the spectrum. In other words, the spectral lines are going to move back and forth. So we see this, as we have this one star coming towards us, we're going to have a blue shift. All right, all the spectral lines will have moved to the blue part of the spectrum. Moves around, okay, if it's moving, perpendicular to the line of sight, to the binary star system, we won't notice any shift. And then as the star moves around and starts to move away from us, we see this same spectral line shifted towards the red part of the spectrum. And so you can see here, following the same spectral line throughout this entire graph here, all right, goes from blue shifted to not, to red shifted, to back to the center where it's not shifted, back to blue shifted, okay? So this is evidence that there's orbital motion, happening with the star, and that there's one star that's moving around another possibly, okay? So those are the three different types of binary systems that you have to know. I'm hoping that you are able to write down everything that I'm saying, all right, for these notes. And again, pause me and rewind me if you need to go over it. But that's pretty much it that you need to know as far as stellar classification goes, okay? Our next section that we're going to be talking about is going to be getting into stellar evolution.